Okay, hello everyone. My name is Shai, and I would like to tell you about a joint work together with Tali Kaufman and Gilles Zemor regarding decodable quantum LDPC codes beyond the square root barrier using high-dimensional expanders. Okay, so let me briefly review some notion from classical coding theory. This talk will be about quantum codes. So a classical code will just be a linear subspace of f2 to the n. And to a classical code, one is also associated a parity check matrix. And the three parameters that we are interested in are the length of the code, which will be n. The dimension of the code would just be the dimension of the subspace, and the distance of the code, which is the minimal Hamming distance of a non-zero vector inside the subspace. And we say that our code is LDPC, namely low density parity check, if each row of the parity check matrix is of bounded weight. So these are notions from classical codes. Now, quantum codes, or the quantum codes that we will be interested in this talk, will be the CSS codes, which are given by a pair of two classical codes, Cx and Cz, of the same length, such that the orthogonal complement of one of the code is contained in the other. So this is the condition that two classical codes need to satisfy in order for them to be a CSS code. And one can also think about a CSS code or the CSS parity check matrix as the two parity check matrices satisfying some orthogonality relation. And for a quantum code, the length of the code will be n, just the number of columns of either one of the parity check matrices. The dimension of the code is described by the following formula. There are several ways to think of it, but it's the simplest way is just it's n minus the ranks of the two parity check matrices. And the distance of the code is actually the minimum of two distance parameters. The first, the x distance parameter, is just the minimal Hamming distance of a vector which belongs to the x code, but not to the orthogonal complement of the z code. And the z distance is vice versa, where the roles of z and x are replaced. And finally, a CSS code is called LDPC if the two classical codes, Cx and Cz, are LDPC codes. So, now, there is a different point of view about how to think about these CSS codes, which is a more geometric point of view. And it goes as follows. So given a CSS code, which you can think of as a pair of two parity check matrices satisfying this orthogonality relation, you can construct from it a two-dimensional chain complex, which is comprised of the following data. You have three consecutive vector spaces, f2 to the rz, f2 to the n, f2 to the rx, and you have linear maps between any two consecutive pairs. So this is del z, and afterwards del x. And the only condition that needs to be satisfied is that these del operators, they're also called the boundary maps. You wanted the boundary of the boundary to be the zero operator. And one of the reasons it's useful to think about this second point of view is because some of the notion coming from quantum coding theory have actually analog using this different language in the theory of chain complexes. For instance, the dimension of the code is equal to the dimension of the first homology or cohomology of the complex. Another example is that the distance of our code, which is, again, it's comprised of the minimum of 2 distance parameters. Each of them has interpretation in terms of notion coming from metric geometry. So the x distance is the cosystole constant of the complex, and the z distance is equal to the systole constant of the complex, where the cosystole constant means the minimum size of a cocycle which is not a coboundary, and the systolic constant means the minimal size of a cycle which is not a boundary. Okay, so this is actually, it's a new language that could be made to be useful depending on whether you understand the geometric object. Okay, so first of all, so I don't want to spend too much time on this slide. So this is just sort of an intuition about 2 complexes, 2-dimensional chain complexes. So you can think of these objects as really coming from a geometric object like a tessellation of some 2-dimensional manifold, or a simplicial complexes with vertices, edges, and triangles, or other geometric objects of dimension 2. And well, it's the example to keep in mind is that you have some, you have your geometric object comprised of vertices, edges, and faces or triangles in the case of simplicial complexes, and you have natural boundary maps. And also here are some common notions from this language. So boundaries are simply vectors that belongs to the image of the boundary map. Co-boundaries are vectors that belongs to the image of the co-boundary map, which is the dual of the boundary map. And cycles, respectively, cocycles, are vectors that belong to the kernel of the boundary map, respectively, the co-boundary map. And the one important remark that I want to emphasize in this slide is that we saw that you can translate a quantum code into a complex, and you can reverse this procedure, giving any 2 complex, I can construct for you a quantum code, and the property of being an LDPC code follows, and it's equivalent in this way to the fact that your complex is of bounded degree. So we're looking for interesting 2-dimensional bounded degree complexes. So here's just a simple example. If you take the following complex, which is the tessellation of the plane with equilateral triangles, and you have the following set of blue edges, then its boundary is the following set of red vertices. And similarly, the boundary of the set of blue triangles is the following set of red edges. Here, the co-boundary of the set of blue vertices is the set of red edges, and the co-boundary of the set of blue edges is the 2 red triangles. Okay, so let's now think or see one example of how geometric objects can give you interesting quantum codes. And this example is one of the most famous examples in quantum coding theory, which is the Kitaev-Tori code. So the geometric object that we have is just a torus tessellated by squares. The length and the height of the torus is some parameter m, we'll see it in a minute. And the quantum code associated to the torus is defined as follows. So each x and hz will be the parity check matrices. The rows of the x parity check matrices are comprised of elementary cocycles or elementary coboundaries, which are simply the edges touching a fixed vertex. So the blue edges here form an elementary coboundary. Similarly, in the Z parity check matrix, its rows consist of elementary cycles or boundaries, where an elementary boundaries are the edges that touches a fixed face. So for instance, here the red edges form an elementary boundary. Okay, and next, here is a non-trivial code word. So here is a cycle which is not a boundary, the blue line, and also a co-cycle which is not a co-boundary. And moreover, because we saw before that the dimension of the code is equal to the dimension of the homology of the torus, should be the homology of the torus, which is known to be equal to 2, we see that our code is of dimension 2, and in fact, we get from the following, from what we described so far, the following parameters of the Kitaev-Tori code. And well, perhaps the task that we are faced is finding now new two complexes that will give us new CSS codes with better parameters that improve upon the Kitaev-Tori code construction. And here I wrote the asymptotic of the Kitaev-Tori code construction. And in order to achieve this goal, there are two directions and two categories of what one can do. So first, one can come up with more interesting geometric objects. I call it the geometrical approach, considering more complicated manifolds than the torus. And another approach is by finding some machinery that gets some small code and output a bigger code. So for example, the product construction that we will mention later on are part of the second category. Okay, so very briefly, let's look at some of the examples in the geometric approach. So instead of the torus, one can look at hyperbolic surfaces. We see that the dimension grows to be linear, but the distance deteriorates to be of logarithmic size. Another approach is to try and take higher dimensional tori, but here, although the constant improves, asymptotically you don't really break the square root n barrier in the distance. Guth and Lubotzky consider higher dimensional hyperbolic spaces. And in that case, again, the dimension is very good, but even though the distance is no longer logarithmic, it's still smaller than square root of n. And the first work that really breaks through the square root of n barrier is due to Friedman, Meyer, and Liu, who considered four-dimensional manifolds and show that you can find in some of them quantum codes whose distance is square root n times log n to the power of 1/4. So they did break the square root n barrier, and this is the record that we set upon to improve upon, and also along the way also get decoding, better decoding procedures. Okay, so this was so far the history of the subject. Now in the remaining time that I have, I want to describe how do we proceed in trying to get better geometric objects. Okay, so the key to, which is also appears in the title, the key to getting better geometric two complexes is using what are called high dimensional expanders. And in particular, the construction of Lubotzky, Summers, and Vishne which we will call LSV complexes. These constructions come from really group theory and number theory, but they were analyzed in the theory of high-dimensional expanders, and we now know a quite interesting feature about them that enable us to get complexes and quantum codes that break through the square root n barrier and also improve upon the Friedman-Mayer and Lu result. And I want to begin by saying just that these complexes are, well, they are simplicial complexes, and they are of bounded degree, and they are explicit in any sense of that you can think of, from a computer science perspective at least, but they are highly complicated objects. They are highly complicated globally, but even locally, it's not recommended to try and draw them on a piece of paper or even to imagine them in your head. So this is an illustration of the local view, the neighborhood of just one vertex of an LSV complex. So you see it's a lot of triangles gluing along edges in a very complicated way. Okay, so I won't get into the actual definition of these LSV complexes. I'll just mention a few facts about them. So first of all, as I mentioned, they are quite explicit. They are Cayley complexes, meaning they are Klee complexes of Cayley graphs, where the groups is the following natural group of projective general linear group over a finite field with a specific generating set constructed explicitly by Lubotzky, Samuels, and Vishne. And a next fact, which I won't dwell upon, is that we can find among all LSV complexes, families of complexes with a non-zero homology. So we get quantum codes which are non-trivial. Next, let me just say that these complexes are quite regular. Namely, every vertex has the same number of edges, namely 2 times q squared plus q plus 1. And every edge is contained in the same number of triangles, which is q plus 1. And I want to say a few words about the local structure of these LSV complexes. So while we don't understand their global structure in the complete, we don't have a complete picture of their global structure, we do understand enough of their local structure, which enable us to get a lot of interesting application and interesting results in high-dimensional expansion. So the local structure of, so first of all, here's a definition. For any graph, define the link of the graph to be the incidence graph of edges containing the vertex V versus triangles containing the vertex V. So this is a small bounded graph, which is q plus 1 regular on 2 times q squared plus q plus 1 vertices. Now, the very important fact is that these graphs are isomorphic to the incidence graph of points versus line of a projective plane over the finite field of q elements. And these points versus line of the projective plane, these graphs are excellent expander graphs. In fact, they are better than Ramanujan graphs. Well, they are not sparse if you think of q grows to infinity, but they do have an excellent expansion property. For instance, their second largest eigenvalue, which is square root of q, for q big enough but bounded, is much smaller than half of the degree of the link. And this property is it's very important. So this is just, I won't dwell upon this picture. Let me just say that the fact that the link of these LSV complexes beat their second largest eigenvalue is smaller than half of the degree gives you all sorts of nice high-dimensional expansion properties. Here is one such consequence, which follows from this local expansion property. It says that if you have a set of edges of bounded size, size is by a fixed constant times the number of edges in your complex, and it also satisfies this reduced property, then the co-boundary of this set of edges is bounded from below by some constant time the size of your set. And what this high dimensional expansion property gives you is that this is a simple consequence of this result is that the x distance of the quantum code coming from these complexes is grows linearly. Already off the bat, we have this linear growing the x distance. Furthermore, we also have the following fact that if you have a set of edges, again, bounded by some constant fraction of all the edges in your complex, and suppose it's not a co-cycle, then there is a local set of edges, all of them in the neighborhood of a fixed vertex, such that if you add this smaller set of edges to your original set, the size of the coboundary decreases. And again, this is a property coming from high dimensional expansion theory, and this property enables you to come up with a local decoding algorithm. And the decoding algorithm for the X errors, it's quite simple. It's just a reiteration of the previous fact. So at each step, you're looking for one vertex and some set of edges on it, which decreases the syndrome, the co-boundary size of your original set of your set of edges in each step, and you repeat it until the syndrome becomes 0. And this gives you a decoding algorithm that corrects a linear amount of the errors. Regarding the Z errors, well, here you just apply standard algorithms from graph theory, reducing it to the Edmonds-Blossom algorithm. This algorithm can only correct up to a logarithmic number of errors, but well, you don't expect for much more because the Z distance of these complexes is not very good. Unlike the X distance, the Z distance is just logarithmic. However, what makes these complexes very useful is the property that if you multiply the X distance and the Z distance, you actually go beyond the size of n. You actually grows like n times log n. And this is a very rare property to come up with. So finding complexes, any complexes that satisfy that the X distance times the Z distance grows bigger than n, these would be very useful in constructing CSS codes which break through the square root n barrier. And the reason for this is due to the balancing procedure, which is originally due to Hastings, and it's also a variant of it was constructed by Tali and Zemor. And the idea is that you have a complex, two complex, such that, let's say, the X distance is very good, but the Z distance is not so good, and you multiply this two complex with certain bipartite graph. And the whole idea is that that this product enables you to balance the Z distance and the X distance. So I'm a bit short on time, so let me just say that these are the parameters that you get from the balancing procedure. And overall, by choosing the graph to be a good LDPC code of an appropriate size, you can, after balancing, you can get CSS codes whose distance grows like n, the square root of n times square root of log n. Again, one can even go a bit further using 3 complexes. So you improve a bit the distance by a square root log n factor, but now you're losing the decoding procedure because we don't know how to decode from boundaries in high dimension. But this was, well, this gave you a slightly better distance. Now, so I'm about to finish this talk, but let me just mention some final remarks. So in all of the analysis, the weak point of the LSV complexes is really the boundary side, the boundary function. And it's a weak point because we have weak high dimensional expansion on the boundary aspect. And we also know that we have weak distance bounds. Another issue is that the decoding from the boundaries is, we don't know how to do it in higher dimensions. But if one is just interested in the distance, well, one might try to look at LSV complexes of higher dimension. And for them, one can show, well, better polylogarithmic bounds on the z distance. The x distance will always be linear for these complexes. The problem is proving that you have a code with some code word in it, namely showing that the homology does not vanish. And in this, and concerning this problem, let me just tell you some recent news, which is available on the archive. It's a result due to Kaufman and Tesler using similar explicit construction, who were able to show that you can in fact get complexes with the following, whose distance is square root of n times any power of log n that you wish. And actually, there is an even more recent news due to Hastings and Hare and O'Donnell, who constructed CSS codes with whose distance goes like n to the 3/5, breaking through the square root n well beyond a polylog factor. And their construction uses a new random construction, which they call a fiber bundle codes. Well, there is some issue there with the weights, whether they are of bounded or of polylog size, the weights of the parity check matrices. But in the case, this is a completely new direction. And again, so this is in the distance aspect, and it's very interesting to ask what will happen regarding the decoding. So far, the decoding result is for the two-dimensional, the complexes coming from the two-dimensional LSV complexes. And yeah, and I think I'm a bit over time, so I'll stop here, and thank you very much.